NL seminar. Good morning. Welcome to this week's NL seminar. Today we have our guest speaker, who's actually from ISI, Mitch. Mithun is a postdoctoral researcher at ISI, working with Marjorie Friedman in the networking and cybersecurity division. Mitch recently graduated from his PhD from University of Arizona before joining ISI as a postdoc. Before that, he worked in the software industry for 10 plus years. He got his master's and undergrad degrees from Birla Institute of Technology and Science, Pilani, India. His research interests include natural language processing, cybersecurity, and quantum computation. So let's welcome Mitch for this talk.
Thank you.
So one more announcement. I think let's keep our questions to the end. Mitch has a lot of slides to go through. Maybe around 11:45 to 11:50, we'll open up for questions. Thank you.
Perfect. Thank you, TG, for introducing me, and welcome all to my talk on quantum natural language processing. So since we have a mixed audience, I will just start with some basic definitions. What is natural language processing? So this is a subfield of artificial intelligence where the specific goal is to make machines understand human language. What is a quantum computer? So it's a rapidly emerging technology which uses quantum mechanics or quantum physics to solve problems too complex for classical computers, like our current computers are called classical computers. And this is the agenda for my talk today. I'll start with what the problem or motivation is and why we are doing this. Then I'll do a quick intro to quantum physics, a very basic one, completely easily understandable. And then I'll talk about what exactly quantum natural language processing is, the state of the art in it, and some open questions I would like to throw out there. So I want to start with a thought experiment. If I tell you the word bank, what first comes into your mind? Is it a financial institution? A bank, right? A financial institution. But why not a bank as a river bank? So there are so many possibilities for the word bank. And we decide what meaning is particularly pertaining to that bank based on the context. Or in other words, if I tell you, I went to a bank to withdraw some cash. So now we know we are talking about the financial institution, a bank. Instead, if I tell you I read a book by the river bank last Sunday, so I'm talking about a river bank by the river, right? So of course, this is what we know as context. The question is, so does just looking at the words around a given word give you the entire context of that particular word? Right. So right now, like I said, I gave you a bunch of words along with it, and you realized a bank means X, a financial institution, which means we were looking at the words around that word bank. But is that how we really think? Is that how humans think? Is it how we understand the meaning of the word bank? What is the understanding? What do you mean by understanding? Is this how humans understand the meaning of a word? Now, the thought experiment I am going to ask you guys to do is from this book called Tractus Logica Philosophicus by Wittgenstein. It's a philosopher. And the question he asks is, he says, that's a penguin, right? What is the meaning of that's a penguin? When we as a human, when somebody told you that picture there is a penguin, how did you arrive at the understanding that it's a penguin, right? So you know or completely understand that it's a penguin only if you know the meaning of the word penguin already. Suppose you have never seen a penguin before, or you have never heard the word penguin before, and somebody comes and tells you that's a penguin. And you're like, I don't know what that means. That looks like a funny picture, but I don't know what that means because I don't have the understanding of the meaning of the word penguin. Now, the question is, what is the meaning of meaning? And this is what Wittgenstein says. Meanings of primitive signs can only be explained by means of elucidations. Elucidations are propositions that contain primitive signs. So they can only be understood if the meanings of these signs are already known. So remember, we started with the discussion of we have a word bank and we are just given a bunch of words around it. But what if you never had heard the word bank, right? So that is how humans learn. Like we already have a rough understanding of various possible meanings of the word bank, and then we pick one of the meanings. So we are not completely relying on the bunch of words around it. So this is going to a big discussion where currently in natural language processing, we learn context using this whole idea pushed by Firth, I think in the 70s, which says a word can be known by the company it keeps. Or in other words, a word can be understood by its context and the words around it. On the other hand, there's a school of thought which says we want meaning as context, which is what we have been thinking about right now. So here we have a lot of these current state of the art in natural language processing using a lot of neural networks, where we have contextualized word representations, which means in a way we are trying to arrive at the meaning using the context which was created using the words around it. So remember, that's the first one, the words as context. We have not yet gone to the meaning as context. Have we, or it's an open question at this point, have we? And the bigger question I want to ask is, do neural networks really understand natural language? What is the meaning of understanding natural language? So these are some of these open questions I want to pose before I start into the talk. Do we want neural networks to really understand natural language? Or in other words, do we want AI to be an augmentation to human intelligence, which probably neural network is doing a great job. It's helping us achieve a lot of tasks. Or do we want it to be a copy of human intelligence? So these are some open questions and thought experiments I want to throw out there before I get into the actual talk. Now let's get into a little bit of quantum physics. So to start with, I want to mention something Richard Feynman said. No one really understands quantum mechanics, okay? So I am going to pretend as if I understand this and tell you whatever little I know, I don't. But I really don't understand this, but still I'm going to try. I'm going to basically go through some quantum physics just necessary to understand quantum natural language processing. To start with, a buzzword you might have heard a lot called quantum bits. So what are quantum bits? Let's start with classical bit. We know we have transistors which go from zeros and ones, and we have entire machines built on transistors called computers, or what we call classical computers. But it's at the end of the day, it's an encoding mechanism which converts everything we say into zeros and ones. But is that how humans think? Humans actually think in a lot of possibilities between 0 and 1. So we have this entire encoding which we are trying to push into the 0-1 world, while what qubit says is, why are we stuck between zeros and ones when there is so much possibility in between that? So zeros and ones, in other words, are just the extreme end cases, while there are so many millions and trillions of possibilities that can occur between 0 and 1. So if you want to really look at the electron levels in quantum physics, you might have seen this in high school where we say that there is no thing called electron particle, it's actually a wave, duality, wave and particle. But the idea here is that this electron is not really staying in one place, it's just floating around. And then when you measure it using throwing some light at it or whatever the experiment is, it manifests into one single place. So that is the whole idea. It's spread all around the place, and then we throw a particular experimenter touches the experiment, and then we get 0 or 1. So there's so many possibilities in between. So qubit, like I said, zeros and ones are just one instance of a multiple n-dimensional possibilities. Now this is the basic tenet of qubits. So the idea here is that the qubits exist in linear combinations of states, also known as superpositions. So what I mean by that is we start with 0 and 1, but there is this whole concept called excited state in physics, where we take it on to this bunch of million possibilities of 0 and 1. So you need to keep an open mind here. This is way beyond our basic understanding of what we have seen around us. So at this point, you have to imagine that the zeros and ones are floating around all over the place with 0.034, 0.051. So there's so many million possibilities. And there are linear superpositions of the basic zeros and ones. So the alpha and beta is something, essentially, we can just say these are like the weights to 0 and 1s. And that's all you need to know at this point. I don't want to scare you more. The qubit can exist in a continuum of states. So like I said, superpositions until it is observed. Now, this is a typical way you write this superposition state. And let me talk about what do you mean by observation. So if we, okay, I'll come back to observation in a second after this. So my point here is there's an infinite number of points on this sphere. If you consider like a bit being thrown around in a sphere, so that in principle, you could store an entire text of Shakespeare in an infinite binary expansion of this one bit, or qubit, right? And when we take it to n dimensions, it's called a Hilbert space. And just some terms I'm going to throw out there. So we are not stuck. Remember, we are not talking about one qubit. They're talking about so many qubits and so many millions. And okay, the million is just a human-induced word. So many infinite possibilities. And that entire infinite possibility is called Hilbert space. And it's a big space. That's why people say that. Don't worry about all that. Just understand the basic concepts. Now, let me come back to what I mean by observation. You might have heard of this experiment called Schrodinger's cat, proposed by Erwin Schrödinger a long time ago. The idea here is that, say you have a box, there's a cat inside it, and there's a dangerous poison which is in a vial inside the box. Now there's a random number generator, in this case a radioactive material, which is, it might drop or might not drop, killing the cat. But the proposition Schrödinger makes is, how do you know the cat is dead or alive until you open the box, right? What if you opening the box is actually causing the event to happen? That is, the cat is possibly dead and alive at the same time until you as an observer open the box. And the proposition which quantum physics tells you is, that's how the world exists, at least in micro level. That's where you have the whole idea of a particle and a wave at the same time. So all these things we see around us are possibly in a continuous state until we as an observer touched it and we collapsed it into one single instance. A very interesting tangent on this is there's a theory called multiverse theory proposed by Everett, which says that we are most likely in one of a million different possible universes. When we took a left turn today, there was another you who took a right turn in another universe. So all these possibilities, all these probability wave functions around us, and there are so many possibilities. Remember, just like the qubit, there's so many possibilities. But you as an observer is the one which is collapsing it into one instance or the other. Why am I talking about this? So this is the basic problem in quantum computation, that we have so many qubits. People are able to push it into this continuous world of million possibilities. But how do we take the knowledge out from that qubit? Because remember, the moment you touch the experiment, it collapses either into 0 or 1. It just basically becomes a classical computer at that point. So this is what people have been trying to achieve in the last 10, 20 years. And great progress has been made in the world of quantum computation because people have invented techniques by which we can manipulate these qubits in their multiple possible states without touching the experiment and collapsing it into the cat being dead or cat being alive, the qubit being collapsing into 0 or 1. And that is the big leap that has happened in the last decade or two, and which is what is triggering quantum computation. So the big question people were asking was how to measure these experiments without touching them. And the short answer is they came up with this whole concept called gates, which is simply based on the gates which we know in classical world, like NAND gate, AND gate, except the idea here is we will not touch the experiment. Instead, we will pass this qubit through a bunch of gates so that we know which stages it is going to go through. So we control the changes that these qubits are going to go through. Or in other words, we are now able to harness the multi-million possibilities that a qubit can go through. Just like a classical computer, we are now telling the zeros and ones, and we are manipulating the zeros and ones, except now we have control in how we want to manipulate it. So now we just got access to this huge possibility called quantum computer, because we are not stuck with zeros and ones. All the calculations which you would have done with 0 and 1 could now be done with all these 0.01 possibilities. So if you're playing chess, we don't have to go through each of these paths like the Deep Blue would have done previously. It goes through all these possibilities one after the other and checks what is the right end game. No, now this can be done together at the same time. And that is what a quantum computer does. So this is a picture from the IBM quantum computer, which IBM has publicly available. Now, there is another amazing property in quantum world called quantum entanglement. And the reason I want to mention this is also very important in quantum computation and quantum NLP. Here's an experiment. There are 2 forks. I take one fork, give it to you here, and I ask you, go to a different continent altogether, right? Just hold on to the fork, go to a different continent. I'm going to keep the other fork with me. Now, then what happens is tomorrow I take my fork and turn it around. Just from facing up, it faces down. What if your fork magically turns without you doing anything while you are sitting in the other side of the world? This is possible. Definitely not on the fork level, but it's definitely possible in the quantum world. And people have known this since 1935. This is a paper by Einstein, Podolsky, and Rosen. And this is what they proposed, that this is called quantum entanglement, that 2 particles are so tightly entangled that you separate them and you do something to the first particle, exactly same thing happens to the other particle. And people have proven this. The latest I know is between Earth and a satellite going around Earth. There was one particle in Earth, they switch the particle, and the particle in the satellite switches. So this is called quantum entanglement, which is why I want you to keep an extremely open mind. This is known for almost a century in physics, but slowly we are now able to manifest it in the form of quantum computation. All right, that was my quick intro to quantum computation. Let's walk into what is quantum natural language processing. Quantum natural language processing, a short explanation, is doing natural language processing in a quantum computer. But the long answer is defining language mathematically so that quantum mechanics can be done in these language vectors using a quantum computer. Now, what do I mean by defining language mathematically? So historically, there have been 2 schools of thought in natural language, in linguistics. The first one is vector space and distributional theory based school versus compositional theory of grammatical type school. The first one is, if you remember, where Firth comes in and he says, we have the whole idea that we have a word and there's context around it. The second school of thought is compositional theory, where we have people like Chomsky and Lambeck who are coming up with this whole mathematical idea called grammar. This has a little parallel to the neat AI and scruffy AI definitions, where neat means we want solutions, the schools of thought, we want solutions which are elegant, clear, and provably correct, like grammar. Is language mathematically provable? Scruffy says, we don't care, we just think intelligence is too complicated, let's get things to work. So which is why we have been doing vector space and distributional theory-based school of thought and saying, yeah, it works. Neural networks is the biggest example. It works, things work. But is it mathematically provable? So this is just an example where, one person says, oh, I have 3 pieces of pizza. And the other person says, here's the math behind it. I have 0.0375 remaining. And the whole neat versus scruffy idea. And we are familiar, of course, with the distributional school of thought, which is we have word vectors. If you are familiar with natural language processing, this simply means now we are able to have meaning of king is close to queen and a man is smaller than king. So these are vectors which we have been able to create using the words, or at least using the words around them. You shall know a word by the company it keeps, said first in 1970s, and which is exactly why we started with, I went to a bank to withdraw some cash. Now, School of Compositional Theory of Grammatical Types asks the question, can we mathematically prove that a given sentence is coherent or makes sense? These are the people who ask this question. What is the meaning of meaning? Is it mathematically definable and provable? What is the mathematically computed value of a sentence like John likes Mary? So now, where does quantum natural language processing come in? Quantum natural language processing is this big breakthrough which is combining these both schools of thought. It's a mathematical framework for unification of distributional theory of meaning in terms of vector space models and a compositional theory for grammatical types. So this is the first time we are bringing these two thought processes together, where we say we are not only going to think that the words are just defined by the words around it, but we are also going to bring in meaning and a logic to it and mathematically provable. So which means, can we compose meanings and also quantify the type of logic? So quantum natural language processing asks the questions, can we compute the meaning of a compound well-typed sentence from the meaning of its constituents? Can sentence meaning live in a single space independent of the grammatical structure of the sentence? Can we use math tools like inner products and tensor products to understand and compare meanings of arbitrary sentences as it is for comparing the meanings of the words in the distributional model? Can we create a mathematical model that exposes how the information flows between the words in a sentence in order to make up the meaning of the whole sentence? So these are the big questions that the quantum natural language processing has been asking for the last decade or two. For example, if I give you a sentence, John likes Mary, and if I give you the definition of loves means something, hates means something, and I tell you likes is 3/4 love and 1/4 hate, can you arrive at a number for which quantifies the meanings of these distinct verbs, love, likes, and hates, propagates through the meaning through a reduction mechanism and comes up with a number saying, yeah, this is 3/4. This is the quantified meaning of this particular sentence. And this all comes from this whole idea that Lambeck proposed called pre-groups. And Lambeck, if you look him up, Lambeck is the last name, he came up with this whole idea of what, if I give you a sentence, tell me if it is a right sentence or not. Does it make sense? And how do you mathematically say that? And he came up with this idea that, okay, here's a math equation. If the answer to this math equation is 0, this sentence makes no sense. If it's positive, anything than that, it does make sense. So now we are bringing in structure to language and mathematically proving that, yes, language has math behind it. Now, how does quantum natural language processing do it? First, what we do is the whole idea that meanings of words are combined to build meanings of sentences, not other way around, which is the original one. We say bank, and then we look around the bank and find what words are there. But this is possibly very close to how humans do. Remember, we said, I first learned what a penguin is. And then you show me a picture and saying that is a penguin. And then I bring the knowledge from the background of my brain and what a penguin is. And now you are showing this picture and I connect saying, yeah, this is the picture of the meaning in my head, which was penguin. Now, the way they define this is the meanings of words are multiple states of qubits. The million possibilities of the word bank is all different qubit states, right? It's not 0 and 1 anymore. A bank could mean X, a bank could mean Y. And imagine this to be so many different qubits, so many different edge or let's say orientations of the same qubit. I should not say multiple qubits. The same qubit is now oriented in so many different waves. I don't even want to say it's location because it's not. It's this big wave of possibilities. So what is a hat? What is a black? What is the meaning of black? Now, how to produce the meaning of a whole from its constituent words? This is the second step. They start with this. Let's consider a bunch of words, W1 to Wn. Each word is in an n-dimensional meaning space, something like what we saw just now for bank. However, the difference is that the dimension is 2 for nouns, while the dimension is 2 cross 2 for adjectives. Now, what do I mean by that? When we have a noun like bank, we can represent, let's say, it in a matrix, let's call it 2, like dimension 2 for a matrix. However, an adjective does not stand alone. Of course, let's say black. When we use the word black, what in itself, there's a 2 cross 2 matrix which has so many possibilities of the meaning of the word black. But an adjective has to act on a noun, a black hat. So now its existence is in an n-dimensional meaning space, which is bigger than that of an adjective. So this is how they are slowly combining the meanings and building it up into sentences. Now, let's start with this. Let's put them all together and take a tensor product and into one big tensor. You don't need to even know any of this. You just have to think, let's take a bunch of random words and put them together in one single, let's say, an array. So let's say Alice hates Bob, right? So now we have a transitive verb hates and 2 nouns, Alice and Bob. So now imagine this big Hilbert space or space of possibilities. Each of these words and their meanings are still existing independently in their own worlds. Remember, we have not even talked about connecting them. These are, let's say, 3 different words sitting in their own meaning space. If you want to talk about qubits, let's say there's 1 qubit for the word Alice with all the possible meanings. Let's put it all together in one vector, and it's sitting somewhere in this big space. There's another vector for Bob, which is in the same dimension as Alice, while there is another vector for hates, which is in a bigger dimensional space. Of course, human brains cannot really visualize this. A bigger dimensional space than Alice or Bob because it needs a subject and an object. Okay, they just happen to be together sitting there in one single matrix or array. And of course, this is what we know as bag of words. These are all disconnected words, right? This is, of course, what current neural network-based mechanisms rely on. Now, how do we as humans make these words interact with each other to form natural language? Or what tool do we use for it? That is exactly what is covered there. So how do we, if we are given a bunch of words, Alice hates Bob's, how are we connecting it and making a coherent sentence? Or in other words, what do you mean by these 3 meanings, Alice hates Bob's, and you did something to combine it, and now we have this new meaning in our head, which means Alice is a person who does not like the person, Bob. And to do that, we use something called grammar. So the grammatical structure is what binds these words together in order to form an entangled whole. We learn this when we grow up, like we are taught grammar in any language, and we say, you don't have to worry about the individual words, but here is a structure, a mathematical structure, and all you have to do is plug and play. You can replace Alice with John, Mary, you can replace Bob with anything else, but we have a mathematical structure called grammar. Now, what quantum natural language processing does is it represents grammar as an operator acting on an operand. It it's just like a function. Let's say we have a function acting on a bunch of numbers, right? So if you want to say like a function which multiplies all these numbers, f of 2, 3, 4, so now the function outputs 24, right? Now, how do we translate this into the quantum world? The answer is entanglement. Remember, I told you this spooky function called entanglement, and this is how they bring the whole idea into quantum world. And the idea is something like this. We take these separate Alice, hate, Bob's words or the meanings of these words, and we throw them into this thing called entanglement. Every time you see the word bell, just remember entanglement. I'm going to leave it there. It's an entirely different topic and discussion by itself. And what I mean by that is, remember the spooky thing I was telling you about? If you take 2 qubits and keep it separate, they are not entangled with each other. You turn one, nothing happens to the other one. But there is a process called entanglement, which can be achieved using a bunch of gates. Like they call it Hadamard and C0 gates. But this is, you think about a classical computer, we take a bit and pass it to an AND gate or an AND gate, and something else comes out. And in this case, consider this as a black box. You send in 2 qubits, they get tightly entangled with each other, and they come out of the other side. If you take one of these qubits and keep it somewhere away, keep it in the moon, keep one in the earth, they are still tightly entangled. And this is the brilliant idea that quantum natural language processing is bringing in and saying that all these words are separate until we send it through this entanglement machine. And this entanglement is what grammar is. The entanglement is what is causing these words to entangle with each other in the meaning space. So now all these separate words are combined together to give you a new meaning. Or let me put it this way. All the meanings of these words have now interacted with each other and have become tightly entangled to give us a new meaning that Alice hates Bob. If you think about it, this is probably how humans think, right? Like we have Alice hates Bob's, 3 different words, and now you see the sentence Alice hates Bob's, and now we have a new meaning coming into our head. And this is what quantum natural language processing does. And their idea is this: grammar is what mediates the flows of meanings between words. Now the rest is all implementation level stuff. So now all they have to do is find the right circuit, like very similar to our chip or integrated circuits. Let's find a bunch of gates, quantum gates, which can encode the information flow of word meanings in a grammatical sentence. So this is like an entire set of papers and a lot of math in there, which I'm skipping through. But they have discovered a bunch of, for every single, let me put it this way, for every single possibilities like adjectives, verbs, they now have defined a circuit which we know is going to do exactly that. And remember, when I say circuit, it's not particularly for the one single noun like Alice. It's like grammar. It's like the structure we are providing, a skeleton we are providing to the qubits and saying that, go entangle yourself and understand the meaning of what she, Bob, hates or Alice means. Essentially, what we learned as kids as grammar, we are now able to map and tell it to a machine. And of course, this is a picture. This is a very complicated picture of a bunch of gates. There is 1 qubit, 2 qubits. Remember, you need 2 qubits for entanglement. So we start with 1 qubits for just the meaning of Alice, Bob, and hates. And then we do entanglement for 2 qubit gates. So yes, like I said, you can always create a bunch of complicated circuits for every single possibility of meaning you want to do. And that's not where it stops. These guys have also taken it to the next level, where called quantum machine learning. It does not directly encode the meaning of words because if you were going in and going to create circuits for every single meaning out there, that's an almost infinite task. But instead, can we construct a framework in quantum states which learns their meanings directly from text? So now we are bringing in exactly the state of the art, which happens currently, which is machine learning. And we are harnessing that into the quantum world and saying, we will start with Alice, Bob, and hates. You go figure out what is the meaning of Alice hates Bob. And this is just like essentially the original back of the paper napkin kind of diagram. So here, this complicated thing is a quantum computer sitting there. And there is also classical computer all sitting next to it. And this is very state of the art in quantum computation right now, because quantum computation currently goes hand in hand with classical computation, where they use quantum computers only for the extreme core task. This is where probably the whole NISQ, the buzzword NISQ, which is noisy, intermediate, whatever, I forgot. But the whole idea is that the machine learning still happens in a classical computer. We send all these learnings to and labels to a classical computer. But every time it learns a new meaning, it gets pushed into this million possibilities in a quantum computer, just like training, which we are familiar with in the typical AI world. Great, theory is great. Does it work, right? I mean, this theory actually was proposed 20 years ago. But now the answer is, these guys that trained the entire Wikipedia onto the quantum computer and finally asked the question, hey, is Chomsky an anarchist? And the quantum computer said 93% yes. So again, so at this point, of course, this is a qualitative question answering session. This could possibly be done by neural networks. But the idea the proponents of quantum natural language processing is pushing is that this machine really understands now the meaning of Chomsky and the word anarchist, and the meaning of the sentence is Chomsky an anarchist, right? So, and because they are mathematically proving that this machine does understand, most likely neural networks also can answer this, but are we sure that it really is understanding it? Can this not be done with neural networks? Yeah, I'm going to refer you to this whole paper by Gary Marcus called Deep Learning, a Critical Appraisal. And one thing which struck me very importantly in this is, there is no natural way to deal with hierarchical structure. Sentences are mere sequences of words, whereas Chomsky has long argued that language has a hierarchical structure. So this is the basic idea which I have been trying to push through into the entire talk. Like, is language mere sequence of words, or is there a much more deeper hierarchical meaning level structure? And this paper goes on to show that there's limited capacity of recurrent neural networks. They cannot generalize rich structure in faithful manner. And of course, every conference in natural language processing you go to, there's at least one paper which comes up and says, hey, here is the reason why we think neural network is not understanding language. And this is one example, right? So there are something called artifacts, which people say are subtle patterns in the data. What if neural network is simply memorizing that every time I see the word Mark Zuckerberg, I have to throw up this particular classification, right? We still don't know, because neural networks are black boxes. And despite people trying to probe into it, the jury is still out on what really is neural network learning. And of course, there's a whole idea called domain adaptation, which simply is that neural networks trained in one domain fails miserably when tested on another domain. So the big question we need to ask is, if the model you're training is truly learning compositionality and meaning, it should have been able to solve the task irrespective of the domain. So is neural network really understanding causation, or is it just doing correlation? This is the picture from 1920s called Clever Hans, which was a horse which could apparently do complex math equations, which was not. It's basically the owner asks 2 plus 2, it picks 4 only because that's like dog training. It was trained to pick 4. To answer this question in a different perspective, can this not be done with neural networks? In classical computers, right? In classical computers, if you want to encode one transitive verb like hate, you need 8 into 10 power 9 bits. Whereas quantum computer, you just need 33 qubits. Remember, when I say 33 qubit, it includes this multiple dimensional space, and a lot of qubits are used for error correction. I'm probably not going to get into error correction now. The advantage of quantum natural language processing is, of course, there is speed up. Like we said, this can be done in this, all million calculations are happening at the same time. It's interpretable because we design the circuits, unlike a neural network where supposedly we design the neural networks, we still don't know what the neurons do. It combines, and most importantly, it combines grammar and meaning like humans do. All right, so before I get into state of the art, I'm gonna probably pause here. It's 11:45 and open for quick questions. Questions, because I've talked the major crux of my talk. Open up.
Yeah. So let's see if we have any questions from our online audience.
Is anybody still awake?
Please raise hand or unmute. Raise hand so we can unmute you. So we see.
Khalil, you see?
We see a question from. Sorry, let me unmute. Khalil, please unmute yourself.
Hi. Thank you for the talk. It was very, very clear. So as a linguist, I'm really, really happy that there is sort of reliance on ideas of hierarchy and so on. Are you assuming, for instance, Lambeck's pre-group grammars, or are you actually learning the grammatical relations from text? So is there any kind of analytic bias built into these systems that tries to use all this work in semantics and syntax on compositionality?
Yes, I thought somebody would ask this question. So yes, so definitely there is entire papers on how Lambeck's, so let me put some names out there. These are exactly the 3 guys who are working in this field: Bob Coca, Mernush, and Stephen Clark. They're all in Oxford and Cambridge. And this work was done in 2010, actually, surprisingly, 12 years ago. And there, in this paper, what they show here is, they start with algebra of pre-groups as a type categorical logic. So yes, they are completely using a partially ordered monoid and the entire, the whole idea. But the contribution of this paper is they rewrite this in quantum mechanics terms. They use this entire pre-group concept, starting from monoidal categories, bringing in a lot of group theory, set theory, and they merge it into the physics side of it. And so at the end of the day, if I have to quantify quantum computation in one sentence, mathematically, all they say is, there's something called U dagger equal to 1, which simply means as long as any 2 matrices follow this whole idea of this, let's call it a math. There's this one equation. Any 2 matrices that follow this equation can be done on a quantum computer. So now this paper, what it does is they take language and rewrite it in such a way that it can reach that mathematics that quantum computer understands. So does that answer your question?
Yes, thank you.
Perfect. Yeah, that's not learned. This is pre-written already, and that's how they arrived at that whole idea of circuits.
Okay, thank you. So we have a question on chat from Shravan Guru Prasad Arif. Let me read it. With the addition of QNLP help mitigate the biases in text, like Microsoft bot that went rogue when it learned on tweets? Since it creates a function model of the grammar, would it be immune to text-based bias, which classical NLP models which do word association face?
Well, my question to you back is bias just an artifact of a data set, or is it a reflection of the society that we live in? If it's a reflection of a society we live in, and you as a human being is learning language and looking at this big bad world, and you're realizing that it's a biased world, and your data set is probably reflecting that. And then the quantum natural language processing is probably going to learn exactly that. Now, can we mitigate it? Possibly. We can probably design a circuit to not understand the meaning of bad things and understand the meaning of only good things. Now, do we want it to? And this will go back to the original question I posed. What do we want AI to be? Do we want it to be an augmentation to the existing human intelligence, or do we want it to be another human intelligence? So these are all big, open questions, if you ask me. Yeah, it's philosophical at this point.
I hope that answered your question. Thank you for the question. Any other questions from our audience?
I ask when if there's nothing else online.
Yeah, priority is to online audience. If there are no questions, then let's see. I don't see any raised hands, so let's.
I just want to follow up on Khalil's question because I didn't really get that from your answer. So it seemed to me when you're talking about there being, it was kind of easier to understand in quantum NLP because you know about the grammar. So, but the answer that you gave, it sounded like it was the grammar that was being developed was just elementary combination. So I can imagine two ways to combine word to entangle, right? You could take a sentence and then entangle every subsequent word, right? So just first word goes with second, then get third word, right? Or you could have a set of grammar rules that you can decide to apply. Maybe you could apply them all, but like pre-written or possibly pre-discovered grammar rules. And I'm not sure which is the way things are done. And if the second category, well, if the first category, then I don't understand where the clarity comes in different from neural networks. If the second one, then I guess I'm wondering about like how you're learning them, or if you're learning them, or if they're supposed to be handwritten or what.
Yeah, so going back to that paper I showed you. So what these guys do here is, let me see. So give me a second. Okay, so this is in this paper, essentially what they do is they take all these possibilities of grammar. Let's say we are acting, okay, there you go. Applying an adjective to noun. So now they come up with a bunch of math and say that, hey, we are creating this bunch of initial grammars and we are giving it to the system and we are rewriting it in terms of the quantum equations. So now they keep going into all possibilities, feeding a subject and object into a verb, and they rewrite that in terms of quantum mechanics equations. So to answer your question, the grammar is already written in terms of the circuits. What the machine is learning is meaning and the combination of these meanings.
So it sounds like a prerequisite is a part of speech tag analysis of the sentence, right? And possibly a role analysis if you're actually looking at subject and object. Before you can actually do this quantum entanglement, right? So you need to know, for example, whether a word is an adjective or a noun. And that's not trivial, right? I mean, consider the word that you use, bank, right? What part of speech is bank? Depends on the context. And so how you combine depends. And so I'm not sure how you get started.
Yeah, so that is deeper math. I need to show you that. And the reason I'm skipping that is, so if we go back to this, the whole idea of pre-groups, right? So, where did that be? So in pre-groups, So the idea here is it's a closed compact category. And what do they mean by that? Where's the paper? Yeah, okay. So John likes Mary. Now, what is it mathematically provable for what do you mean by John likes Mary? And this is grammatical because of the following reduction. And the reduction is that there is N, John, and there's something on the right side of N. And then there is a transitive verb likes, and there is NL. So together, this math happens, right? And I'm not at all well-versed in the pre-group grammar. I read through this, did not understand much.
I mean, this looks a lot like a CCG.
Yes. If you're going back to the math side of it, and then they're saying they're gluing it together, and then can we model this language in a concrete category, right? So math comes in, if you ask me, like set happens, set theory happens, monoidal categories, and then say non-commutative, compact, closed categories. I don't understand this. I don't understand pre-groups. I don't understand language, but I got a rough understanding of what they're doing. Okay, that's where my answer stops. I can probably go through this. I've gone through this paper at least 20 times. I'm still going to go through and understand this a couple more times, how they, do the tensor product and understand and bring it to the quantum level.
So there is concrete software, right?
Yes.
Okay, so maybe this is a way to get around this is, what do you need to provide in order to use their software?
Yes, good question. So
like in terms of the data.
Yeah, so this is probably what I was going towards. So these guys they made it public, okay? They made all the experiments public. And if you look at this, it's just one pip install away. It's called DiscoPy. And you really just provide these words, okay? The word is NR, who is NR, and things like that. And this toolkit, interestingly named after Lambeck, it goes through this particular sentence, does the encoding for you, and rewrites in terms of the quantum circuit and TensorNet. So it is doing this understanding math in the background.
Can you go to that? The notebook is informative here, right? So here you're saying is that Alice is a word of type N, loves is a word of type N dot R at S N dot L. So it's that you're applying CCG like categories. Like, right? What I mean is that's a thing that forms a sentence that takes an N to the right and an N to the left. Right?
Yes.
This is the whole semantic parsing kind of thing. It's a very small case, of course.
So these are all toy data sets.
Yeah. It's the ambiguity is where things get interesting, right? Is where you have multiple different possible CCG categories, and those get exponential for verbs, right? In terms of the kinds of sentences and
So my understanding is my rough understanding is these possibilities of grammar is also encoded by this multiple qubit states. So I know we were talking about meaning at this point, but I'm going to go on a limb out there, and I'm going to say this is possibly also encoded and captured by the qubit. I don't know that, and that's my guess. Okay, I don't know the answer to that. I can probably dig deeper into this and answer it. Okay.
I have a question. So when I think of language, I think of like two branches, semantics and syntax. So here now with the quantum NLP or quantum computational linguistics, the grammar part is not learned. In these examples, it's a circuit. Correct me if I'm wrong. The syntax part is expressed as a circuit, quantum circuit, whereas semantics is expressed as entanglement. Is that correct understanding? Okay, so now the task or example you were showing, the grammar is encoded by parsing. I saw a block diagram where there's a parser. So the circuit has to change from language to language, right? So the machine has to be generic enough to encode any circuit.
Yes, I don't even think they have even thought of multiple languages. They're still struggling with English, from what I understand. So yes, possibly eventually getting there, different languages, different grammar. So yes, short answer, I think yes.
Okay, and the syntax part is considered as solved problem. So you have some tools, you can just use them.
That's what I understand from the circuit or the string diagram, which we saw just now, where the pipeline, where they say, yes, you give English, we have the standard parser, uses CCG or whatever, and we come out with a circuit. that's where my understanding stops.
Okay, great. Thank you.
Can I quickly run through the rest of the slides for a couple more minutes?
I
So
think we have 2 more minutes.
Yeah.
I'm gonna have to step out. But
okay, so just wanted to mention this like state of the art in quantum computation. We have IBM Quantum saying we have 65 bits, Google saying 53 bits, Microsoft says 65 bits, and there's apparently like a news article from last month which says plans to offer access to 1,000 qubit processor by the end of 23. Don't know what that means. Even ISI has a quantum computing center. I don't know anything about it, and I don't know how many bits we have. This is open source. Interestingly, IBM has an open source toolkit called Qiskit, where you can harness their own quantum computation. They've just made it publicly available, like on a Google, on an Amazon cloud. And within 5 years, supposedly, we have better quantum computers. Not going to get into error correction. But remember, even today, this is an article from last week, which says ordinary computers can still beat Google's quantum computer after all. So yes, it's a very nascent field, not doing great. And like I said, this field of quantum natural language processing is exactly like 2 years old, implementation wise, at least, and very nascent, exactly 3 people working on, including me 4. So this is a pipeline we saw. Currently, we have only qualitative results, nothing to explicitly say that it beats neural networks, is better than neural networks. So they have the whole theory called quantum advantage, and we are only here, like speed up for some NP hard problems, NP problems, let's not go into hard. And there is all these possibilities which people want to go through. And yeah, this is the breaking crypto systems is already achieved. Quantum machines can break regular crypto systems. I want to end with some open questions. Are we going towards a known devil versus unknown angel scenario, where we know neural networks are flaws and possibly is not completely understanding language, but is that enough motivation to switch to a new technology? On the other side, if meanings is what humans use to understand language, why are we using neural networks, which seem to be using words for understanding language? Will QNLP be the neat word merges Cruffy's moment? Is there a true quantum advantage? Now, what I mean by that is there a problem in natural language processing that can be solved only by a quantum computer and not by a classical computer? And are there any other benefits of QNLP apart from the speed up or the higher accuracy? I mean, speed up is great. Things you do in 1 day, they can do in 1 second. But is that really a reason to switch to a new technology? And the answer to that is going back to Church-Turing hypothesis, which says any algorithmic process can be simulated efficiently using a Turing machine. And there's a modified version of this also, which says simulated efficiently using a probabilistic Turing machine. So, given enough time and memory, we should probably be able to solve any problem. So I don't know if there is a problem that exists. And the other question I want to ask is, are neural networks really like dogs, which are like essentially doing something to please their masters, but they're not really understanding the meaning of sit? Are they? Or are dogs understanding it? Are quantum computers going to understand it? And going back to the big question of, do we want AI to be an augmentation to human intelligence or a copy of human intelligence? So my basic idea when I gave this talk was to start a bunch of thought-provoking questions. And if I have been able to make you do that even for a second, I have succeeded. If yes, keep quantum. Thank you.
Thank you. Thank you, Mitch. We have a few announcements. So one, if you want to have a meeting with Mitch, reach out to us or reach out to him directly on Slack or email. And 2, we have 3 intern talks scheduled for next week. So see you next week.
All right, guys. Thank you.
Peter, stop recording. Thank you.
I don't know what got